Glad to see you still running.
Yeah. Yeah, especially after you go on roading.
Yeah, maybe we have to toss the solar race too.
I Toyota several times on it on purpose.
Yeah, the car cost us $2,000. Here, cost us $13,000.
That over there, so when they get hungry, we'll actually watch the sunny rise. Watch the sunny rise when the day's coming, right? So.
Oh, yeah, yes. This would be.
Next week.
Okay, good morning. My name's Dooling, I'm the Education Director, and I think about half of you already know that. And what we're going to do today is celebrate what Richard Towsey did 70 years ago, kicking off observing the sun from above the atmosphere. We'll start people wandering in. So what he was doing is taking us up above Wild Blue yonder, with the first instrument carried by a rocket from White Sands Proving Ground. Very simple spectrographic instrument, really good design because the V2 rockets we were using at the time for upper atmosphere research did not have really good attitude control. Basically, they were designed to pitch the warhead on the V2 from here from 100 miles into Belgium or England or France. They weren't really designed as scientific research instruments. So his spectrograph, cleverly designed, had a couple of little tiny fisheye lenses, little tiny sapphire spheres that acted as fisheye lenses. So no matter just about any direction the rocket was pointed, it would capture sunlight, focus it into the optical train up to a grating, which then dispersed the sunlight, spread out the spectrum like a rainbow. You get the same effect if you look at light coming off of a DVD or a CD and down onto a strip of film. And this is what he came back with. Second try. First try, the picture there, he was picking through the remains of his instrumentation after the first attempt, just augured into the desert and he didn't get anything back. Second attempt, got this, and the measurements are in kilometers, so it's up to a little more than 30 miles altitude, and it's in the ultraviolet portion of the spectrum. So this is up beyond an energy what the human eye can see. So starting from 2 kilometers, the elevation at the launch pad, up to 55 kilometers. So human vision is from here over there, and what you can see is as it goes higher, and there's less and less atmosphere blocking the view. We're picking up more and more ultraviolet. In particular, now we're picking up ultraviolet that's absorbed or reflected by the ozone layer up in the stratosphere, the protective ozone layer that everyone worries about. So this was a fundamental step forward. It gave us a view of the sun that we hadn't had before. So why would the Navy, Towsey was from Naval Research Laboratory, why would the Navy worry about what kind of energy the sun was producing? One of the reasons goes back to World War II, is also how we wound up with the Solar Observatory at the Sunspot. That began as one of the first Air Force space weather forecasting stations, observing the sun, because in World War II, we started to realize that solar activity could disrupt communications on Earth. Actually, all the way back in the 1800s, there had been solar storms, in particular the infamous Carrington event of, what was it, June 1842? 1842? 59, excuse me, 1859. Massive white light flare that put the telegraph system on fire in London because of the induced currents. Operation Cerberus, 1942, Nazi warships broke out of port in Brest, the west coast of France, dashed up the English Channel in broad daylight, caught the British, the Royal Navy, the Royal Air Force, everything completely off guard, partly because they did it during daylight instead of sneaking through at night when it was expected, but also because there was coincidentally a geomagnetic storm that partially hammered the British radar. So you could look out in the channel and see the ships, but the radar just couldn't pick it up. So you come forward to rockets, nuclear weapons, jet aircraft. By golly, you want to know what's flying around, what's coming, and be able to stay in contact with your sources. So this was a major concern for the U.S. And Soviet military. Space weather hazards, driven largely by the sun. I'll talk a little bit more when we get down to the end, but even today, with the advanced, if anything, the advanced technologies we have now make us more vulnerable to space weather effects than in the past, because the electronics are smaller and they're more sensitive to damage that might happen. People like to talk about, I've got more computing power in my cell phone than we had in the computer that took us to the moon. True, but if you're going to the moon, you want the computer that took us to the moon, not your cell phone, because that thing's going to get fried in about 24 to 48 hours by radiation. Yeah, you'll have a little paperweight, except there's no weight in space. Okay, so getting to know your local star, a little bit about the sun. Relative to Earth, 109 times the diameter. If you go up to the National Solar Observatory Sunspot, where I used to work, Sunspot solar system model, 18-foot diameter geodesic dome outside represents the sun. You can walk in and see the cross-section of the sun. Earth would be a 2-inch diameter ball by comparison. So it's really big, 333,000 times the mass of Earth. The important part that makes it really interesting is solar magnetism. And they like to say in the business that if the sun didn't have magnetism, it would be as boring as people used to think that it was. Okay, so discovering it, first sunspots were observed as early as 800 BC by Chinese court astronomers, really more astrologers. This is a much later depiction since he's using a telescope that didn't exist back then. And these are in the court records, but they didn't really pursue them. So pride of discovery goes to our favorite cranky old astronomer, Galileo, who discovered them about 400 years ago and provided observational data along with Fabricius and Scheiner that really established that this is a phenomenon on the face of the moon. It's not imperfections, the face of the sun. It's not imperfections in Earth's atmosphere, which a lot of people, earlier observers, had thought Earth is horrible and corruptible, the sun is perfect and unchanging, therefore the spots must be something in the atmosphere. Because they didn't have a long-term observational set of data, drawings and so on, it was easy to write it off that way. Galileo established that what was going on is it was something on the sun that rotated with the sun, indicating it was a spherical body, and he could see the sunspots evolve with time. What caused them? That was one of the big mysteries for the next 300 years. Another idea to give you a sense of scale, size of Earth relative to sunspots, size of Earth relative to coronal loops. Yeah, and the thing to keep in mind is when you see this, and you see this, you're seeing magnetism at work. One of the activities I'm working up is called dark side of the sun. The dark side of the sun is magnetism. One scientist has called it the sun's dark energy problem. You can't see it, all you can see are its effects. Okay, more discoveries of the sun. Fraunhofer, 1814, discovers absorption lines in the solar spectrum. This is actually recreation of the solar spectrum by one of the instruments that used to be operated up on Kitt Peak. But instead of the spectrum being continuous, the way Newton discovered it when he refracted light in the 1600s, Fraunhofer, as he's spreading it out, starts to discover these little black bands where it seems like the light drops out altogether. Those are absorption lines, chemical fingerprints. And research on Earth, Bunsen and Kirchhoff established that it's unique to each chemical. And this is how we were able to start figuring out the chemical makeup of the sun and of other stars.
Okay.
Sunspot Cycle, oddly enough, was not discovered until the mid-1800s. The data were there staring at everybody, but nobody had actually done a account back and forth of what was going on. Schwab was actually looking for Vulcan, a hypothetical planet between the Sun and Mercury. About something far more important. The sunspots came and went on a roughly 10 to 11-year cycle. So he figured that sunspots possibly were in some of the drawings that had been made, and so he's tracking things very carefully, and he and his assistant, I believe it was his wife, noticed that the spots seemed to come and go in this roughly 11-year period. And when we look back at historical data, Schwab and Wolf found that indeed that was the case. Although the 11-year cycle is not always there. Jack Eddy in the 1970s researched historical data and found there was actually a period of 70 years when named the Maunder minimum after a British scientist and his wife who made the initial discovery, that indeed it appeared that the solar dynamo just sort of went to sleep and there were virtually no sunspots for what we now know is 3 complete magnetic cycles. So the 11-year cycle is really half of a 22-year magnetic cycle. The sun's north and south magnetic poles with flip sense. 1908, the big discovery. And for my money, George Ellery Hale should have gotten the Nobel Prize in Physics for this one. He determined that what was happening inside sunspots is intense magnetism. So those absorption lines I've mentioned that Fraunhofer had discovered almost a century before, if you looked inside of a sunspot, instead of 1 line, you got 3. Okay, just 10 years earlier, a Dutch scientist, Peter Zeeman, had discovered that if you had a strong magnetic field imposed on a hot source, instead of getting 1 spectral line, you would wind up with 3 of them. And the spread of those lines would give you direct measurement of the magnetic field. This told Hale that the magnetism inside the sunspot had an intensity of 1,000 to 2,000 times the strength of magnetism here on Earth that makes our compass needle turn. And remember how big those sunspots were? It's that intense across the sunspot, sometimes even stronger. So everything in solar physics since then, for the last century, has been increasingly driven towards understanding magnetism and what's going on with it in the solar atmosphere. Okay, sunlight. Sun is not actually a simple yellow disk, as a lot of us might like to think, because that's the impression that our visual system gives us. It emits in a very, very broad part of the spectrum. This little term is something that really confuses a lot of basic astronomy students. Black body. How can you say the light from a black body? That's kind of an oxymoron. Okay, actually what's happening is it's so bright, it's not reflecting any of the light that might shine on it. The light that's shining on it is just insignificant by comparison. So this is the range of colors, if you will, the energies that a black body is producing. Your body would have a black body signature. It would be very wimpy, just barely down there, but it gives us a measurement of the energy of the star. And we like to talk about the sun having a peak temperature of about 5780 Kelvin, almost 10,000 degrees Fahrenheit. But what this tells us is that there's a lot going on in the infrared. There's also interesting stuff going in the ultraviolet, which is part of what Richard Towsey was after with the instrument he launched 70 years ago. Problem is, our atmosphere blocks that off. Blocks off most of it. You can see a little bit of it, but not that much. So you see, this would be the ideal. That's what the sun's actually producing. This is what the atmosphere will emit at sea level. So you can see there are actually some sections they just get blocked out altogether. Oxygen, water, oxygen, carbon dioxide, the atmosphere just makes it completely black. This is why, for example, the new 4-meter telescope that the National Solar Observatory is building is not up there. They would have loved to have built it at Sunspot, but the seeing conditions weren't just good enough. They're building it on top of Maui, 10,000 feet altitude, really good seeing conditions. Okay, so scientists knew that the atmosphere was messing up the view, and there was a quest for altitude to get higher. In particular, Samuel Pierpont Langley, who was the 3rd secretary of the Smithsonian Institution, then Charles Greeley Abbott, the 5th secretary, conducted a number of observations of the sun. In fact, Langley invented a basic instrument that we still use today, more advanced versions called a bolometer. That just means it measures everything that an object, all the radiation that an object throws at you, all of it. And he went to mountaintops, really did also trying to establish the solar constant, because at that time we still believed that the sun's total output was unchanging. They were trying to get a handle on that. And what they finally concluded, I think it was really neat, he had all this data wrapped up around a can of cans of Mother's Oats, that there was still too much atmosphere above where they were observing for them to give a conclusive answer. And it turns out that the numbers they came up with their estimates were a little bit higher than what we have now. Okay, so higher and higher brings us forward to Towsey, his rocket launch in 1946. And we're going to talk about 3 types of missions. The suborbital ones I'm just going to do briefly. Then we're going to talk about the satellite missions. We still do suborbital. That's where you just get up above the atmosphere for a few minutes, parachute back down. Usually it's done here because you want to be able to recover the payload. Doing it out of Wallops Island or other facilities, lands in the ocean, a bit more problematic, so it's a lot easier here. Was not able to get a total count from NASA, but they're flying these days about 5 per year in 2 categories. One, this one just flew back in July, and we took some of our campers out to see it when the payload was being worked up. A neat little instrument called High Seat looking at the corona, and it's kind of hard to make out, but this is an image made with a telescope on board Solar Dynamics Observatory. This was made with the instrument on board High Seat, and it's a lot sharper. So we do 2 things with sounding rocket flights. One, test out new telescope techniques, new telescope designs. It's relatively inexpensive to find out if it's going to work or not before you put it on board a spacecraft and you go, whoops, we just made a $250 million mistake. Here you only make maybe $5–10 million mistake. Secondly, the other category are copies of instruments that we already have up in space. And at least 2 a year out of White Sands are in that category. Just one, sometimes, yes, sometimes it's 2. I've seen it.
No, they do 1 a year.
Is it only 1 a year? Okay. Basically, you have a carbon copy of the instrument that's up on SDO, Solar Dynamics Observatory, and you fly it and you compare the measurements between the 2. Because you're sitting there staring at the sun 24 hours a day, 365 days a year. That's brutal. So the old-fashioned fudge factor that we would use in our lab classes in high school to make the answer come out to what we knew it was supposed to be is what they're working for there. You can live with the instrument degradation so long as you can characterize the instrument degradation. And the funny part is the part of the instrument that's decaying is different from what they had expected. So once a year they pull it out of bonded storage, they fly it, recalibrate the measurements. So that way the data that you're getting now and 5 years ago and 5 years hence will all match up. Balloons we've used a lot. Stratoscope 1 in 1957 carried a 12-inch diameter telescope, and it gave us the first really sharp images of granules, these circulation cells in the visible surface of the atmosphere. By the way, when we talk about the visible surface of the atmosphere, it's not solid. It's actually thinner than the air that we're breathing right now. This is simply the point where the solar atmosphere has gotten thin enough that light has a better than even chance of escaping into space instead of being reabsorbed right away. So this is like the radiator panel for the sun. This is where it starts losing energy. This is where we get all that circulation and turnover and part of the production of magnetic fields and sunspots. So 1957, it's still, we're carrying advanced instruments, Sunrise, earlier this year, and we're working on being able to launch these down in the Antarctic, have a circle the South Pole so we get a week, maybe 2 weeks of continuous observations with the instruments. The reason we do this, again, suborbital rockets and balloons, it's cheaper than satellites. So sort of an in-between point. Okay, bragging rights for the first orbital instrument to study the sun goes to the Soviets. The Sputnik 2, wasn't just like it, the dog, they also had a gamma ray instrument to measure solar and stellar sources. Our first satellite with solar instrumentation was SOLRAD, which actually turns out was a spy. It was a signals intelligence satellite that the Navy launched. The X-ray detector for studying the sun was the cover story. And it did produce valuable data. I think it was about a dozen or so SOLRAD satellites were flown over the years, and they produced good, valuable initial data on the sun. But this was primarily signals intelligence, which the government has declassified. Okay, the first dedicated missions, orbiting solar observatories, real interesting design. This would spin, this didn't. So it's called a D-spun platform, and we had several X-ray instruments mounted in later versions, coronagraphs. Coronographic telescopes basically produce artificial eclipses inside the telescope. And this is not to get really pretty pictures like the whiz-bang stuff that you see coming out of eclipses, and the one that will, the total eclipse that will go across the U.S. In about a year. It's because those wonderful, beautiful, delicate arcs of light you see in eclipse images, they're not delicate. Those are immensely powerful magnetic structures rooted deep inside the sun. So looking at the corona tells us what's going inside the sun, but it's so faint, it's really difficult to do that on the ground. It's a real specialty. Doing it in space is much, much easier because you don't have the atmosphere cluttering up the view. Okay, Sol Wind came out of that OSO series that NASA launched. This one is somewhat infamous because in the 1980s, it became the first satellite shot down by an anti-satellite weapon. So it was an EOD satellite, P-78-1, so the Air Force owned it, they could do with it what they wanted, and they claimed that it was old, creaky, it was on its last legs, so they shot it down with the ASAT launch from an F-15, really sending a message to the Soviets, look what we can do. They said, you know what, this thing is lousy, it's rickety, it's not doing any good. Actually, it was still observing. Dave Rust at Johns Hopkins University said that he was watching a coronographic image coming in, and it just goes to snow. Lost it right in that frame. Okay, a class of satellites I'm going to skip over altogether. Orbiting geophysical satellites, OGOs from actually Explorer 1, remember, that should be 1958. Explorer 1 discovered the Van Allen radiation belts, and the OGO series were launched in the 1960s. This is a relatively recent launch by NASA studying the magnetosphere. So these are studying the effects of solar activity on Earth. Completely different talk, so I'm not going to go there. So I just want to mention those. Why I'm skipping over them. Okay, now a lot of satellites carry solar instruments as hitchhiker payloads. In some cases, for example, upper atmosphere research satellite, if you're going to be studying what the atmosphere is doing in response to solar activity, you need to look over your shoulder and see what the sun is doing. Geostationary weather satellites and also polar orbit weather satellites carry little solar observatories mounted on the solar rings. This is going to be pointed flat onto the sun all the time. May as well put a small telescope there and monitor solar activity. So that is part of the National Space Weather Forecasting System, the Space Weather Forecasting Service up in Boulder, Colorado. So this is the GOES-R satellite that's going to be launched soon, and those are the instruments mounted there. So you can see this is really big. You know, compare that with the instrument that Towsey flew, was about this big. Look, this is the size of a hitchhiker compared to a man. Okay, back to dedicated satellites. One of the biggest ones was Skylab. So we tend to think of it in terms of astronauts living and working and doing experiments in space. The Apollo telescope mount had 8 telescopes mounted in it. Coronagraph, ultraviolet, X-ray, and a couple looking at the sun in H-alpha, a deep red color that we observed that will help us track solar magnetic activity. Bottom right there, Owen Gary is at the control panel for the ATM and provided us with a lot of fundamental insights into solar activity. And again, you might ask if we can see in deep red from Earth, and by the way, the highway going to Sunspot 65, 63, that's the wavelength in angstroms of that deep red color, H-alpha. Even though we can observe it from the ground, again, from space, it gives the imagery sharper. 2, it gave them something to match up with the ultraviolet X-ray images and coronagraph images that they were taking. Some of the missions have gone into solar orbit. Pioneers, I believe, was 6, 7, and 8 went into solar orbit. Helios missions were designed by Germany, launched by the U.S., went into solar orbit. So, and they're not carrying telescopes, but they're carrying instruments like those geophysical observatories to measure the electrical fields, magnetic fields, the electrical particles that are being spewed out in solar wind. Solar polar mission went over the North Pole and then the South Pole of the Sun, because we're in equatorial orbit essentially around the Sun, can barely see what's going on at the poles, big mysteries of what's happening. Turns out the solar wind is moving out a lot faster from mid-latitudes up towards the pole than it is down near the equator. One of the more famous solar missions, Solar Max. Famous because, A, it was a large dedicated mission, provided a lot of useful data to the science community, but B, more famous to the public because this is the first satellite we picked up and repaired. It was designed for it. The bus down there was designed so you could take an entire module off and replace it, which is what they did. Here, Pinky Nelson is trying to dock with Solar Max. Couldn't quite do it. There's a little mismatch between the attachment hardware he had and the fitting on the satellite, but they were able to retrieve it with the robot arm. And one of the things they did on it was open heart surgery. Yeah, open heart surgery. They were repairing the electronics for the coronagraph, and the panel where they had to do that bit of work on the insulation that was covered up because it was going to be launched on Valentine's Day. The ground crew drew a heart, and that was where they had to cut. Other nations, Japan has contributed 2 significant satellites, Yoko in 1981, which looked at the sun in X-rays, and I'll mention the other one in a moment. I'm kind of going chronologically here. Manned missions resumed with, science missions resumed with Shuttle and Space Lab. Space Lab 1 had some solar instruments, including measuring the solar constant, mounted out here on the pallet. Space Lab 2 had 4 telescopes looking at the sun in ultraviolet, coronagraph, and looking at the relative abundance of helium in the sun, and also the ultraviolet, looking at what is the output in different channels, narrow parts of the ultraviolet spectrum. And then some of these instruments wound up getting reflown as part of Atmosphere Terrestrial Laboratory series that was flown on Shuttle. And sometimes, like for example, this one, Susum, just flew by itself, mounted on the side of the Shuttle. That was one of the neat things about Shuttle, was that it was easy. What the managers told me, the neat thing about little secondary payloads is they're real easy to manifest. The bad things about secondary payloads, they're real easy to de-manifest. So it's easy to get on board, but since you didn't have the highest priority, if they decided something else needed a bit more weight, you got bumped. And this is an example of one of the secondary payloads that they flew, Spartan. This was an intermediate point between sounding rockets out here and the full-blown telescopes mounted on the instrument pointing system and so on Space Lab. So this was basically a sounding rocket payload on a little satellite box. Shuttle robot arm would pick it up, toss it over the side, they come back 2 days later, recover, it's completely autonomous, and you get the data back. Flew a total of, I believe, 4 times on Shuttle, 3 of them very successful, and one that didn't succeed was because they had a procedural error, didn't get it started up properly. But this was a really neat way to do science, solar observing at a relatively low cost. They had some schemes at one point for even more advanced stuff. The Space Lab 2 payload was supposed to be flown as SunLab, but that would have been after the Challenger accident and everything changed. Plus, that was one of the last times that we really used film in observing. At this point, it was the era of solid-state detectors coming in, so that changed everything. But at one point, they wanted to have a 1 meter, 40-inch diameter telescope, solar optical telescope, fly on shuttle, and then eventually put it on a manned platform where you have an array of instruments. This would have basically a very sophisticated pinhole camera for looking at the sun and X-rays, and that edge would be the disk for coronagraphs, so you could create an artificial eclipse for a camera down here. Didn't come to fruition, unfortunately, and one of the scientists I knew in Huntsville even proposed this monster solar observatory on the moon. This thing is so retro that initially I thought it was a 1950s concept. And Alan Gary told me no. In fact, you can see the NASA worm there on the side, so that establishes it as 1980s. Okay, back to instruments in space. SOHO, European Space Agency, again, international partners have been very busy. It does not orbit Earth so much as it orbits the Sun. It's at a gravitational balance point between Earth and Sun. So you just have to tweak the position every now and then, but basically it's sort of riding in this null area, and you get dragged along. The neat thing about it is that you are in front of the Sun. The moon's never going to get in the way. Just one antenna, always pointing back towards Earth. Wonderful stream of data coming from it. In particular, the two coronagraphs. This is just one coronagraph image, so that's the Sun. They have 3 coronagraphs on there to look at the corona in different levels of faintness as you got farther and farther out. Only 2 of them worked. The one that the U.S. provided unfortunately went belly up in very short order after launch, but it still has provided a phenomenal amount of data and images. And yes, you look at that, that's a comet. Yet sun-raising comets were discovered by the orbiting solar observatories, and literally hundreds of comets have been discovered with imagery from SOHO, including a number that have made suicide dives into the Sun. So that has helped change our view of the solar system. SME, solar mass ejection imager, another hitchhiker. Really interesting way of looking at the solar wind. You can see what they did. You would scan, you would block out the Sun itself, because that's not what you want to see. You want to see the solar wind as it expands outward and comes towards you. So you have to block out the Sun, which is at least 1 million times brighter, and then you subtract the stars, and what you get is an image of the faint cloud coming out. So this was an Air Force instrument hitchhiked on an oceanography satellite about 10 years ago. Unfortunately, it's no longer operating. I don't know of any follow-up plans on it. Small Explorer class missions designed just to look at very specific problems in the Sun. Transition region, trace transition region in Coronal Explorer. The Sun, as you move from the surface, the temperature in the space of about 100 miles or so just soars from a few tens of thousands to millions of degrees as you go into the corona. This is still one of the outstanding mysteries about solar activity. Why does it suddenly jump and get so hot? And you'll read a story about, at least every 2 years, sometimes once a year, mystery of solar coronal heating solved. It's been solved about 12 times, and when the hoopla dies out, no, we know a little bit more about what's happening, but we still haven't really figured it out. Source is a really important one, and again, go back to the instrument that Towsey had, and this is just designed, has a series of different bolometers to look at the output of the Sun in ultraviolet, visible, and infrared, and give us really detailed measurements across many parts of the spectrum, because the output of the Sun is about 1,368 watts per square meter per second. Okay, that's the total output. But sometimes it puts out a little bit more in the X-ray than it does in the visible and the infrared. And X-rays and visible and different parts of infrared affect the atmosphere in different ways. So it's not even, it's almost like whack-a-mole. It's a little bit less output here, a little bit more there. And this is one of the things we're trying to come to terms with and understand. Solar B, Hinode, Japanese satellite, 20-inch diameter telescope, and I've always considered its original name as a neat unintentional pun, because in physics, B is the term that we use for measuring the strength of a magnetic field. Solar A was Yoko, that I showed earlier. Solar B is designed to measure solar magnetic activity in detail, and it was renamed Hinode, sunrise after launch. Stereo, this one's really terrific. As the name suggests, 2 satellites to look at the sun, give you stereo imagery. So they put one into a solar orbit that's a little bit higher than Earth, a little bit farther away from the sun than Earth, so as a result, it would start to fall behind. The other one was put into solar orbit a little bit closer to the sun, just a hair closer, so it would wind up moving ahead of us. So this gave us imagery of the sun from increasingly great angles and eventually on the backside. Now, not total coverage on the backside because it can't transmit through the sun. It's extremely noisy. And one of the satellites we lost contact with, we just got it back. So that thing may yet be healthy. And that's an example of the kind of imagery. So here, we've got a coronal mass ejection going on. For example, you might be able to see only edge on from one position, but you get this wonderful structure, figure 8 or symbol for infinity, depending on how you want to read it, off on the side. This is the one that's really blowing everybody out of the water, Solar Dynamics Observatory. So that's an array of, I believe it's 8 solar telescopes and 4 containers, plus other instruments. It's in geosynchronous orbit, almost overhead. So it's off that way. And that figure 8 pattern is because it's not exactly in geostationary, but it's inclined slightly to the equator. So it just traces out this figure 8 pattern constantly. And all the data go down to the relay station out next to White Sands Test Facility. So if you ever go out there, there are 2 large antennas, always pointed slightly to the southeast, south by slightly east. And it's just sucking in all the information from that satellite. Multiple views of the sun, the visible photospheres, like we like to think about it, magnetic fields, and then ultraviolet up into the edge of the X-ray spectrum. When NASA was launching it, the press releases talked about multi-channel HD TV of the sun, 24 hours a day, and I thought, wow, this is a bunch of NASA PR baloney. Well, about a year later, I'm exhibiting at the Solar Physics Conference, and these people set up in the booth next to mine. They ate my lunch. They set up a 60-inch plasma screen TV and still couldn't put the entire disk of the sun on there at 1:1 pixel resolution. This is 4K by 4K stuff they're cranking out. It really is multi-channel HD TV from the sun. So I'd urge you, just Solar Dynamics Observatory. Pardon?
150 megabits per second.
Yes, that's why it has the dedicated ground station out at Wistiff, just for the fire hose of data that's coming down from that. Again, the most recent missions, this is actually a really quite tiny satellite. It's only about 7 feet long. And it's looking at what goes on in that region where the solar atmosphere starts to move from the photosphere up through the chromosphere, so-called because it was a bright red color when first observed in eclipses, and into the corona in very fine detail, because there's a lot of energy transfer, a lot of energy change going on that we don't fully understand. Okay, so how far have we come? Again, going back to Towsey's real simple spectral images, 70 years ago, these things on film, and they didn't just print it like this. They used a densitometer, basically something that measures the optical density, how dark or how light are the images. Used a densitometer across here so they could get the relative strengths. And the paper was published literally within a matter of weeks in an astrophysical journal. That's a phenomenal turnaround for back then. Okay, so there, Towsey, multiple disk images of the sun. Magnetic fields, black and white, continuum, that's basically the visible surface, and then we're up into the ultraviolet. This is at the near the upper end of what the human eye can see, so this is actually close to blue light. rather than yellow. Yellow would be down around 550, that's 4,500. And then higher and higher energies. Here, 10 billion degrees, the regions where flares are produced. And then you can combine those images, and all those arcs there are computer representations of the magnetic fields. So just incredible advances that we have made since Towsey flew his instrument. A lot of it, yes, of course, obviously due to computers. They can just process gigachunks, if you will, of data to produce stuff like that. And you can tell by the artificial colors, this is several different SDO images being put together. And at the same time, if you're studying something that's a great beauty shot, if you're going to sell the program to Congress, but at the same time, you're going to use imagery from IRIS, imagery from ground-based observatories. And I'm giving them short shrift here, and don't want to forget about them because they still play a very, very important role, especially the 4-meter that's being built up on Maui. And we're going to go even closer. 2018 Solar Probe will launch, and we'll spend about 6 years doing flybys of Venus, gradually cranking the orbit around so that its aphelion, its low point compared to the sun, gets closer and closer, so it'll actually be well inside the orbit of Mercury. And it'll be come to within about a quarter of the Earth-Sun distance. That'll be the closest that any man-made object has gone to the sun. It has a ceramic heat shield system and actually 2 sets of solar arrays, because by the time you get in that close, the solar array that's used out in deeper space would simply be overpowered, so they're going to have a smaller, more robust solar array.
And they fold them up when they get close to the sun.
Fold them up. And this is not going to have any telescopes on. It's mostly going to be fields, electrical fields, magnetic fields, particles, and so on, but also even just measuring the shift, the change in pitch of the radio signal as it's orbiting the sun will give us some insight to the interior structure, how the gravitation, how uniform or non-uniform the gravitational field is. Okay, so what have we learned? A lot, since stuff like that was done. Okay, space weather effects are really, really serious. I mentioned the telegraph system being set on fire. That's the one we like to point to a lot, but also later solar storms in the late 1800s turned on, would activate with power, put enough electricity into the telegraph system in the southeastern U.S. that the operators could just disconnect the batteries and run it on the power that Mother Nature is doing, because it's just a wire, a long copper wire. Okay, you think in those terms, power grid, wires running for long distances, pipelines, metal tubing running for long distances. Anything like that is going to be susceptible to energy being input through the magnetosphere and pumped around as a result of geomagnetic storms. Now some of this is activity that is driven by Earth, but a lot of it is driven by the sun. And we don't fully understand the coupling mechanisms and how everything works. The way stars twinkle at night when you look at them, the ionosphere does that to GPS signals. Yeah, the ionosphere will do it to GPS signals. And remember, GPS does not tell you, satellites do not tell you where you are. They're not aware of you, they don't care. All they do is tell you where they are and the time of day. But if that signal gets twinkled, if you will, by changes in the ionosphere caused by solar activity, now your unit is going to tell you you're over there instead of here. And a mistake like that, even just a couple of 100 feet, can be fatal for an aircraft that's relying on GPS for precision approach. Okay, the Coronal Wind, discovered by Orbiting Solar Observatory 7 and really defined by Skylab, comes out of coronal holes. The solar wind comes out of coronal holes. These gaps, these relatively cool regions, where it just seems to escape. So rather than being constrained by magnetic activity, where we have these gaps, it seems to flow out. Solar constant. We quit using that term in the early 1980s because the sun isn't constant. We now refer to total solar irradiance because there are slight variations. And one of the challenges is that, again, wicking the sun is really brutal, and doing it with the kind of precision that we need is almost impossible. So you wind up with the instruments, like these two are looking at the same thing at the same time, same thing here, and even this is a copy of that one. It's measuring quite different. That's okay. You just select one as a 0 point and you line them up. And here we see variations in solar activity from 1979, or 1980, when Solar Max was launched, through today. And the 0 line, so 1367, that's the average we take. The 0 line for on this graph would be down in the ground floor. And one of the things that we found is that total solar irradiance varies in step with sunspots. So it's kind of counterintuitive. The sun's brighter when it has more spots and dimmer when it has none, because the magnetic activity causes a lot more emissions in ultraviolet and X-ray. Okay, the solar corona is very, very hot. Temperatures going up into the low millions of degrees. Surface of the sun, 5780 Kelvin, about almost 10,000 Fahrenheit. You get into the corona, it's soaring up to millions of degrees. Why does it suddenly rise like that? This is one of the findings that came out of OSO, the Skylab. And the dynamos that produce the magnetic fields are really far more complex than we imagine, really fine scale structure. In fact, one scientist at Lockheed referred to the solar magnetic carpet, because it's like looking at the fibers that make up a carpet. You look at it in finer, finer detail, you find finer and finer structure to the threads and the way they curl, the warp and the woof. And for you to understand how that whole carpet works, we have to understand how those individual threads work. And between the lower and middle atmospheres, there's a lot more complexity going on. So this is Iris, produces an image, and then it has a spectrograph, kind of like what Towsey had, that just scans back and forth across one tiny area that's being studied to try to understand with a microscope what's affecting the sun as a whole. Okay, so what do we still need to learn? Okay, so Skylab showed us that the solar wind is originating from the coronal holes, but we still don't understand that mechanism and how it's becoming the solar wind. A little bit of insight that one scientist got earlier this year from Scario is that apparently the solar wind starts out nice and smooth and then starts to break down, kind of like water coming out of a faucet. Nice steady stream, but as it gets further and farther from the faucet, that stream will start to break up into large droplets. Very rough analogy, but basically that appears to be what's going on with solar wind. Another image from SDO, coronal mass ejections. Those are those big magnetized gas bubbles that the sun likes to belch at us periodically, usually during the solar maximum. How do they evolve as they go across the solar system? And this is important again to space weather, because if one of these hits us, squeezes Earth's magnetic field, now you've got major geomagnetic events. You have operators shutting down satellites to protect them. You're going to have power grids, maybe disconnecting parts of the grids simply to keep a large voltage rise from going across large parts of the system and cause blackouts like we had back, I believe it was, what, 1984, 85? 89. The Hydro-Quebec blackout. And then the solar dynamo. So it's not just at the surface. Solar magnetism is more than skin deep, because we've got circulation along the base of the convective region up to the poles and then back down. At the same time, the sun is rotating faster at the equator than it is at the poles. And it's like the cat, after a while, those magnetic field lines look like a cat's been playing with a ball of yarn. It is just completely tangled up. It can't be straightened out. Essentially, the system collapses, resets itself. Magnetic north is now magnetic south is magnetic north, and you start with the next 11-year cycle. And apparently, sometimes this dynamo will not fully express itself all the way to the surface, and that's when we have a modern minimum, an earlier Sporer minimum, where the dynamo is still working, but it's just not coming out to the surface, and we're not getting sunspots, so it's reduced to solar activity. Okay, quick tour of the sun, bit of a fire hose of information. Dave Hathaway, Craig Forrest helped me out with it, plus my 9 years at NSO gave me the background for this. Questions? How did I do on time? What time is it anyway?
Noon.
Noon? Okay. Thank you. 15 to 45 minutes, okay, not too bad. Yes?
Hi. The Northern Lights.
Yes, sir.
Or auroras.
And Southern Lights are Aurora Australias.
Correct. Well, in any event, I understand that that signal doesn't come at the speed of light. How much lead time does one have looking at the sun and say, oh, gee, I'm going to get up there to Alaska and look at these guys? How much time have you got?
Anywhere from a few hours to a few days, depends on my favorite all-purpose two-word answer, it depends. Okay, as he said, the aurora borealis, the signal doesn't arrive at the speed of light because it's not light that's producing it. It is charged particles from the sun, as the solar wind, gusts from the solar wind, hit Earth's magnetic field, which has electrified particles, charged particles trapped on the field lines. They zip back and forth merrily. They'll come burrowing down towards the North Pole or the South Pole, hit a mirror point, make a U-turn, go spiraling back and forth. You squeeze it, you energize it, you force that point, that reflection point further down. Now they're hitting the atmosphere. When they hit the atmosphere, they give up their energy as light. So when you look at the aurora, you're looking at Mother Nature's TV picture tube. That maps out what's going on in the magnetic tail, which is 500,000 to 1,000,000 miles downwind out towards space, because it's compressed by the solar wind on the sun side, dragged out on the anti-sun side, the downwind side. Okay, so it's energized particles. It's not the ultraviolet or the X-rays produced by solar flare or coronal mass ejection, but it's the energized particles that come from that. They come sailing across the solar system, they hit us. The sun has to be pointed in the right direction because the sun's rotating, so it's a bit of a lawn sprinkler effect as it's moving out. So if something is pointed straight towards us, is going to wind up missing. Something over here is going to hit us. And that's one of the things we're trying to work out is which, and for example, with the solar mass ejection imager that was blocking out the sun so they could see the faint gust coming towards us. Which ones do we have to look out for? Which ones are going to be the most damaging? My best suggestion, if you wanted to go up to Alaska to see the aurora, or up to Canada, would be to wait until we've got relatively active sun and just plan on spending a week or two. Because
A week or two, so you have a week or two.
right, so well, not a week or two advance warning, but a week or two just to have a better chance of catching one. You might be up there for 2 weeks.
The duration of this is a week or two.
No, it's not that the duration is a week or two. It's that you might have to wait a week until, just by chance, you get the right one. During solar maximum, yes, you probably have pretty good odds of seeing one within 2 or 3 days or maybe continuously. During a period like solar minimum right now, you're not going to see that much. You have to get further north in order to see a relatively wimpy aurora.
At this point, where we are, you won't hardly see it at all.
No, it would have to be a phenomenally powerful event for the, basically if you think of almost like the oval, the magnetic oval at the north and south poles, almost like a real big powerful rubber band, it would take something really powerful to stretch that down and drive particles at lower and lower latitudes. So if we see an auroral event this far south, which is not unprecedented, it has happened, it was something really powerful. In 1960, we went to Arlington for my grandfather's funeral. NASA was launching a barium tracer payload out of Wallops Island. So we're standing out in the parking lot of the hotel, looking to the southeast, hoping to see this cloud created by a barium tracer that was going to go up into the ionosphere. Massive aurora to the north of us. Story in the paper, while everybody was looking for the rocket launch that got scrubbed, they missed the aurora right behind them. So, when it's going to happen, and of course prediction back then was much cruder than what it is now. I'd probably give you a better chance of tonight's Powerball numbers.
I'm sorry?
I'd probably be better off predicting tonight's Powerball numbers than telling you exactly what the aurora. Just go during maximum, and you have better chances of seeing something while you're up there. It's like going whale watching. There's no guarantee that the whale's going to broach. You might see nothing. You might see an entire pod hit the surface. So it's just roll the dice and see what comes up.
But you had the time of year you would go up.
Well, not the time of year, but time of year in winter would be better.
Right.
The longer nights. But, and I've seen the aurora once. If you go to Alaska, try to book a seat on the right side of the plane.
Yeah.
Okay, because now you're facing to the northeast, and you can see the auroral oval. You can see auroral activity, which I did when I flew up to Anchorage in 2004. If you're on the left side of the plane, you're looking at the southwest, you're not going to see anything. And it was quite beautiful. So yeah, during solar maximum in the winter, that's your best chance. Yes?
What's it look like from a plane? I've seen it from the ground because I was in northern Wisconsin a month or so ago, and we had it up there because I thought, oh, the street lights are on in this town about 50 miles away from us, and then I realized, no way. Then I went down there and looked, and it was all white, and then started seeing the veils. So.
Yeah, it was white veils in the distance, and it wasn't fantastic view because I still had to crane my neck a little bit, but it was quite pretty, and it's still pretty similar to what you see from the ground because it's at a distance. It's probably several hundred miles out since we were cruising at about 35,000 feet altitude. Now, what's really neat is the view that the astronauts get from the space station because their orbital inclination takes them up very close to the auroral ovals north and south. And if you look at those, Aurora, space station on Google Images or something like that, and you'll find some really stunning images, stills and videos of the aurora. NASA also has some satellites, Image and others, that have instruments designed to look down at the aurora, not just invisible light, but also charged particles, protons and so on, reflected back to give them a better view of what's going on. And those data also go into space weather forecasting.
Now, what about the colors? Because I've seen it in colors. It's just, not just green, but I've seen, the reds and so on.
It's chemistry. It's atmospheric chemistry. Which electrons are getting energized, and then when they drop, they get energized. When they give up that energy, it's going to be in a very specific color, unique to that particular atom and molecule. Again, those Fraunhofer lines. Those showed as absorption lines, but if the gas is cold with a dark background, when they get energized, those will show up as emission lines, which is basically what you see with the aurora, is the entire area just emitting in one or two colors. Quite stunning. So that could be another talk to give in the next year or so.
Yeah.
Yes?
You said something about an eclipse in the United States next year. Is it going to be a total eclipse?
Total eclipse, totality. Totality will start, Jim, you've probably tracked this closer than I have. It's going to run roughly northwest to southeast, go across Wyoming.
Yeah, it'll start over in Portland, and then kind of zing across Boise, and then dip down through Nebraska, Illinois, and then into North Carolina.
And we get, what, about 25% totality here?
We're going to have about 70% here.
Oh, that high?
Yeah. And that, but yeah, if you get up over within that, it's about a 200-mile wide region, and that's where we're going to get totality.
And in solar observing, eclipses still serve a purpose because the disk of the moon acts as a wonderful knife edge that first covers up and then uncovers solar features, so you can watch how quickly they disappear and then reappear. And this can give you a more precise measurement of how small something is than what you could do with your telescope. So there's a phenomenon in the atmosphere of the sun called bright points. I showed you sunspots, and they kind of look like sunflowers with petals, is penumbra, where the magnetic field is leaking out. And then those circulation cells called granules are about the size of anywhere from New Mexico to Texas. That's how big they are. But we get these little tiny bright points in there. And the question was, are they, kind of that big and reasonably bright? Are they really tiny and phenomenally bright? And the answer is really tiny and phenomenally bright, because what we did was watch during the transit of Mercury how quickly they would extinguish and then come back on the trailing edge. Yes?
More comment about that. As most people have never seen a total eclipse, and they don't realize that the Muslims' flag represents a total eclipse. It's an explosion. You won't, unless you've seen it, you don't really understand how significant it is. And it's really an explosion. It's worth going to see is what I'm trying to say.
Yeah, and by the way, practice eye safety wherever you're watching it. Because the sun is blocked out, it's easy to think, oh, it's safe to look directly at it. And you know what, technically speaking, if you're looking at it right at the moment of totality and the disk is totally blocked, yeah, it's safe. But you can get a misperception of how long that moment or period of safety is, and you wind up looking at the unfiltered sunlight, especially coming around the edges, and it can cause eye damage. It's permanent. The retina you've got is the one you're going to live with forever, so take good care of it.
What month is this going to happen?
It's what, August next year?
August 21st.
August 21st?
Right, and Jim and the amateurs will be set up here, and we'll have an outreach activity. That, I think right now, I'm supposed to be
Well,
figuring out.
we're all going to Wyoming.
Oh, you're going to what? Okay.
There isn't a motel
Okay, well-
left in Sheridan.
Okay, we'll get some shoe boxes and punch pinholes in them, and there you go.
There's still campground spaces.
Very few left.
Yeah, I know.
I did have one last question. There's conjecture that the Egyptian wise men didn't worship the sun, they actually studied it. They were solar scientists.
I had not heard that one. It'd be nice to see some evidence supporting it. It's interesting.
Well, one of the things I read is there's clues that this is probably occurring, because why does it say in the Bible, if you go back to the original manuscript, before King James Version, you can find the 666 has a decimal modifier at the end. It's 66.6, which happens to be 3 solar cycles.
That's interesting.
Now go read Revelations 13 again, the last verse. It says it takes a wise man to know that a man's lifespan is 3 solar cycles. That's what it says.
I'm 66, my time's up.
That's it.
Okay, it's been nice talking to you. I gotta go check out.
Regarding the ramp up and the coming off of the peak of solar maximums, is that curve somewhat constant, or do you find that there are, maybe we had a 6 month, from low sunspot activity to bam, and then maybe it extended out a year or 2 after solar maxima? Does that vary, or is that somewhat consistent?
They vary. They vary. Even saying 11 years, it's varied. It's been as short as about 9.5, sometimes upwards to 13. More than one solar physicist has wrecked his career by saying solar cycle, ta-da! And then the next cycle is completely different from what you predicted.
Because we do have that tendency as just regular folk to say, hey, it's an on-off switch.
It's not
solar
on-off.
cycle 24, and then bam, it's 1 month or 6 months.
There's even one school of thought that it is inherently chaotic, and we will never be able to predict exactly what the next cycle is going to do.
And while the sun averages 11 years, other stars that time can change, and that given information that we now have from Kepler sampling 150,000 stars, you can see that solar cycles on other stars will go anywhere from 5 to 15 years. Ours just happens to be about 11.
Right, it has to do with the size, the chemical composition, the age, temperature, etc. One scientist with the National Solar Observatory in Tucson, Mark Giampapa, the deputy director, did a study of the solar cycles of sun-like stars in the M87 cluster. And one of the things he found is that things like the Maunder minimum are apparently a part of the normal life cycle. That every now and then, we can't predict when yet, the Dynamo, as I said, sort of takes a snooze. It's still working, but it's not expressing itself all the way to the surface, and you don't get lots of solar activity like we had in the 70s, 80s, and 90s. In fact, classic solar event, August 1972, massive solar flare, right between the Apollo 16 and 17 missions. If we'd had men on the moon when that flare went off, we could have lost the crew, or they certainly would have been greatly increased. They would have had radiation sickness and greatly increased risk of cancers later in life. So Kathy is champing at the bit to announce that I will be the next speaker.
Yes, you will. And please, Dave, tell our audience what you'll be speaking on.
Obviously, we're inducting Gene Roddenberry next month, so I guess it's going to be Star Trek themed. Actually, yes. It's the 21st century, it was promised warp drive. I see no warp drive. Where are the warp drive starships? Where? Okay, where's my warp drive? It's going to be looking at, take a quick look at rocket propulsion, which is what we're stuck with for the foreseeable future. Some of the alternative, or frankly, fanciful drives that have been suggested, and an actual honest-to-goodness warp drive concept that Miguel Alcubierre at in Mexico City has worked out that's getting some attention in the physics and engineering communities. I won't give everything away.
Thank you all for coming. As Dave said, we will be inducting Gene Roddenberry on November 12th. That'll be in conjunction with our 40th anniversary celebration. If you'd like to attend, we'd love to have you. There are limited tickets available for the event, and you can sign up online at our website. And I must also say that if you are a museum member, you get a discount. Just saying, so that you know. Yeah. We'll have some special guests, which will include Harrison Schmidt as our guest speaker. That evening, we'll also have David Stipes, who is an Emmy Award-winning special effects expert that worked on Star Trek: The Next Generation. We'll have David Gerald, who wrote probably the most famous Star Trek episode, The Trouble with Tribbles. And we will also have a gentleman named Bill Kraft, who is a dyed-in-the-wool fan that spent 13 years of his life fighting with the United States Postal Service to get Star Trek commemorated on a stamp, and he finally succeeded. So we should give him a lot of kudos. We'll have a silent auction that evening of a variety of autographed items as well. So I do encourage you all to come and join us for that. Thank you very much, and we look forward to seeing you at the next Launchpad lecture.